Divide a circle's circumference by its diameter, and you get pi. It starts simply enough as 3.14, but as you calculate further, it expands outward into an infinite string of decimals with no repeating pattern and no end. It is a mathematical constant that refuses to resolve. Looking at the analog screens in this mid-century control room, you might assume space exploration requires millions of digits of precision. In reality, agencies like NASA only need about 15 digits of pi to navigate probes between planets. If you want to calculate the circumference of the entire known universe, and you want your math to be accurate down to the exact width of a single hydrogen atom, you only need 37 digits. After 37, the physical universe runs out of space to measure. Yet in December 2025, an engineering team at StorageReview flipped the switch on a highly specialized server and let it run continuously for 4 straight months. Their sole objective was to calculate pi to 314 trillion digits. To run this calculation, they built a machine with dual AMD Epyc processors, totaling 384 cores, 1.5 terabytes of system memory, and a staggering 2.5 petabytes of scratch storage. A petabyte is equal to 1 million gigabytes, and scratch storage is the temporary memory a computer uses to hold data while it's actively working on a problem. The sheer mass of the resulting data was almost unmanageable. The final file containing those 314 trillion digits weighed in at over 130 terabytes. To make it available to the public, they had to partner with a cloud infrastructure company, Backblaze, just to host the colossal output. This leaves us with a stark disparity. We are burning megawatts of electricity, monopolizing physical server racks, and spending months of computational time to find trillions of decimals that have no practical mathematical use in the physical world. The obsession with pinning down pi comes from its mathematical classification. Pi is both irrational and transcendental. Irrational means it can never be written as a perfectly clean fraction, like 22/7. Transcendental means it cannot be solved using standard algebraic equations. It simply refuses to be contained. Around 250 BC, the Greek mathematician Archimedes tried to trap the exact value of pi physically. He drew increasingly complex geometric polygons, shapes with straight sides, both inside and outside of a circle, calculating their perimeters to squeeze the value of pi into a measurable range. For centuries, this infinite, non-repeating messiness deeply frustrated engineers and politicians. They wanted clean, easy-to-use numbers for their blueprints and textbooks, not an endless string of chaos. This frustration reached its peak in 1897 inside the Indiana state capitol. The state legislature introduced House Bill 246, which attempted to legally redefine pi to a flat, easy-to-use 3.2. Politicians literally tried to legislate the geometry of a circle to make the math easier. The bill actually passed the state house unanimously. It was only stopped in the Senate because a visiting mathematics professor from Purdue University happened to be in the building, overheard the debate, and intervened before the government could officially break the laws of mathematics. Human authority cannot simplify pi. Its infinite, unyielding complexity is a strict law of the universe, and we are forced to work around it. This diagram illustrates the breakthrough that finally moved us past drawing physical polygons. The infinite series. These are equations that add or subtract a never-ending sequence of fractions. The longer you run the series, the closer you get to the true value of pi. This mathematical framework was perfectly suited for the first generation of electronic computers. Instead of humans spending decades doing arithmetic by hand, we could program machines to run these loops of addition and subtraction endlessly. By the mid-20th century, massive, room-sized mechanical and early electronic computers took over. In 1949, the ENIAC computer spent 70 hours calculating just over 2,000 digits. But as machines got faster, the reason for calculating pi began to change. Because the digits of pi are entirely random but mathematically absolute, checking a machine's pi calculation against the known sequence became the standard for computational stress testing. In the 1990s, a mathematician running a high-level number theory computation noticed his machine was returning incorrect answers. He traced the error down to a physical hardware flaw in a commercial computer chip. The math was perfect, but the silicon was broken. The pursuit of pi had shifted. We were no longer calculating billions of digits to learn more about the geometry of circles. We were using the absolute mathematical truth of pi to hunt for physical flaws in our own technology. This brings us back to the 314 trillion digit record in 2025. When you push the stress test to the trillion-digit scale, you hit an absolute physical wall. This schematic shows the problem. At this scale, the processor's ability to do the math is no longer the issue. The real barrier is the system's storage bandwidth. The CPU calculates numbers so fast that the storage array chokes trying to read and write the intermediate calculations. To bypass this bottleneck, the StorageReview team had to alter the server's architecture. They removed the standard PCIe switches, the hardware traffic cops that usually route data on a motherboard, and wired the CPUs directly to 40 high-speed solid-state drives. This allowed them to maintain a massive data transfer rate of 280 gigabytes per second. The system had to maintain these extreme thermal and bandwidth limits continuously for 4 straight months. If a single drive failed, or the memory dropped a single bit of data over those 120 days, the entire 130 terabyte output would be mathematically ruined. Compare the sheer physical weight of that setup, the petabytes of storage, the thousands of watts of continuous power, the custom cooling systems, against the simple 37 digits of pi required to measure the edge of the universe. When we push pi to 314 trillion digits, we aren't learning anything new about mathematics. We are measuring the absolute physical limits of the machines that will build our future.